We'll start up in just a minute. Okay, let's start here. Welcome, everybody. My name is Charles Leiterson, and I will be lecturing this class with Professor Jonathan Reagan Kelly.
It's nice to see everybody. I'm excited to be here for what's actually my first class teaching at MIT. I actually did my PhD here about 6 years ago and just rejoined the faculty. I've been a few other places since, so I'm excited to be back and excited to join you all.
This semester promises to be unusual. I certainly have never lectured in this fashion before, but I hope it will be less chaotic than last semester. Professor Reagan Kelly and I are both committed to ensuring that you have the best possible experience in this class, despite the pandemic. I want to dive right in and tell you what the course is about before we do all the administrivia and such. And then Professor Reagan Kelly will dive even deeper with a case study. So this is a class about writing fast code. And so you can ask, why are we studying performance engineering? Why write fast code? If you talk to a lot of people, they'll say performance isn't that important. And indeed, there are a lot of software properties that are more important than performance. But to gain some perspective, let's think about what they might be. So here are a few. Correctness. Does the program provide the right answer? That certainly seems more important to me than performance. Functionality. Does the program do something interesting? Security. Is the program resilient to malicious attacks? What are some more? Please respond on the lecture Slack channel. Here it is. And just put in some of the words that you think are important. I see maintainability, readability, stability, simplicity, modularity. These are great. Scalability. Oh, 2 scalabilities. Great.
It's a scalable answer.
So here's just a few I wrote down, some of which you folks said. And I'm sure that if you put your mind to it, you can produce a whole lot more. And these are arguably more important than performance. So that raises the questions. If these properties are all more important than performance, why study performance? There are a lot of other classes out there. You don't have to take 6172, and it's not too late to drop. So this, to me, I thought was a confusing question. And whenever I'm confused, which is more often than you might think, I often find that an apt analogy can help me reason my way out of my muddle. I kind of intuitively feel performance is important, but all these other things seem more important. So what's another thing that we want, which we're happy to trade away for things that are more valuable to us? What do we want, but we're happy to trade it away for things that are more valuable? Money. Here's the analogy. Which would you rather have? A gallon of water or $100? Now, water is essential to life. And in fact, if you're in the desert, you might prefer a gallon of water to $100. But in normal situations in today's society, I bet that you would pick $100. Whoops. Why? Well, duh, because you could buy a gallon of water for $1 and have $99 left over to buy other things. You didn't get into MIT without being able to figure out stuff like that. You choose the money precisely because it can be traded for things you want more. And in fact, as we say, water is essential to life. Money is not. But this is what economics teaches. That prices are driven by supply and demand and not by intrinsic value. And we sometimes would rather have something that we can exchange for something that's more important to us. So we'd rather have money because then we can buy all these things that we might want that are actually more valuable. Sometimes a gallon of water is more valuable than $1. So go out and I'll trade $1 for the gallon of water. So in this sense, performance is the currency of computing. It's not as valuable in some ways as all of these other properties, but you can often buy needed properties with performance. For example, when Steve Jobs originally produced the Apple Macintosh, they devoted a spectacular fraction of the processor capability to the user interface. He bought a slick interface with performance. And history has generally shown that we can always use more performance, and more money. So at this point, I'd like to just take a break and see if there are any questions on the Slack channel about why we study performance. So any questions there, Jonathan?
Yeah, one or two are just coming in.
Oh yeah.
So Hope asks, is there anything you can't buy with performance?
Sure. There's things you can't buy with money. There's an old Beatles song, "Can't Buy Me Love." And is it ever true that code is written so perfectly that you can improve performance? Yeah, sure. There's sometimes when things, but what typically happens is it's diminishing returns. The amount of effort you'd have to put in to improve the performance isn't worth it. And this is something you need to learn in doing the projects in this class. At some point, you can spend hours and not have much progress. And you've got to understand, okay, I've done as much as I can do in the time I've got. Okay, so let's talk a little bit about history to get a better perspective on performance engineering and see how we got to where we are today. In the early days of computing, machine capabilities were limited. Programmers did a lot of performance engineering simply trying to make code run fast enough to be useful. So here are three systems. Look at the clock rates. In 1964, it was 33 kilohertz. Today, it's 5 orders of magnitude faster. Your computer runs around 3 or 4 gigahertz. And over time, resources improved, and computers got way cheaper. But since computing was expensive, it was worthwhile crafting code to make applications run fast. You programmed around the machine. And for some things, they wouldn't even fit in available memory or in the amount of time needed to run a real-time task or whatever without intense performance engineering. But things changed because people realized all those other properties that I mentioned on the other slide were more important than performance. So Bill Wolfe was a famous compiler expert, and he said, more computing sins are committed in the name of efficiency without necessarily achieving it than for any other single reason, including blind stupidity. In other words, be careful about trying to make your code run faster. Michael Jackson, famous for his work on software development methods, as well as, I guess, his distant cousin, Michael Jackson, the deceased singer, said, the first rule of program optimization, don't do it. The second rule of program optimization, for experts only, don't do it yet. Turing Award winner Don Knuth said, premature optimization is the root of all evil. Now, it turns out this quotation has been widely misinterpreted, but the misinterpretation shows what the field has generally thought of performance engineering. When Knuth said this, he was actually defending performance engineering. He was saying that it should not come right at the beginning of code development, but later in the process, when it's possible to identify which parts of the code are taking the most time. Now, Knuth is a giant of computer science who has made many contributions, including creating the field of analysis of algorithms, defining modern asymptotic notation, developing TeX, the typesetting engine behind LaTeX, and, which is particularly relevant for us, inventing the first performance profiler. But at the end of the last century and the beginning of this one, performance engineering was largely neglected in university curricula. And there was a good reason for it. So let's see why. So here is a plot of technology scaling. Each dot in this figure represents a particular microprocessor. The horizontal axis shows the year, and the vertical axis shows the number of transistors in the given microprocessor chip. Now, this has all been normalized to, I think, like 1972, it looks like. Now, the growth of transistor count was astounding. In just 50 years, the capability of our computers grew by 5 orders of magnitude. And the key process behind this growth was miniaturization of the circuitry. Integrated circuit components just kept getting smaller and smaller thanks to the semiconductor industry. This trend, a doubling of transistor count every 2 years, is called Moore's Law. I'm sure many of you have heard about this. And it was observed and articulated by Intel founder Gordon Moore in the 1960s and 70s. Now, Moore's Law is not really a law. You can't get arrested for breaking it. But the semiconductor vendors treated it as if it were. During this time period, up to about 2004, clock speed grew fast as well. A lot of these transistors went to making computers run faster. And this period is often called the Dennard scaling era. During Dennard scaling, clock period increased at an annual rate of about 25 or 30%. Every year, your computer not only would get more capable in terms of more memory and such, but the clock period, actually the clock frequency increased. I guess the clock period went down. So the clock frequency increased at an annual rate of about 20. The clock period improved at an annual rate of about 25 or 30%. Okay, that's astounding. That means every year you got free performance. You didn't have to write complicated code to get performance. You just waited till next year and you got an automatic 30%. We have some projects in this class where you'll be happy to get 30%. And you can see the effect in the advances in hardware. So here are 3 machines released by Apple that all cost about the same amount. So in the late 1970s, the Apple II had a clock rate of 1 megahertz. 13 years later, the clock rate had increased to 400 megahertz. And just 4 years after that, to 1800 megahertz. Computation just kept getting cheaper and cheaper. So Moore's Law, miniaturization, and the scaling of clock frequency was a printing press for performance, which is the currency of computing. Every year, your software would run 25 or 30% faster without you doing anything. Your old code just ran that much faster, and that continued for about 50 years. So let's take a break and see if there are any questions at this point. I see somebody coming through. Okay, we'll move on. Oh, here we go. What about improvements in algorithmic bounds and their impact on the field's performance? Algorithmic bounds for some problems has actually been quite remarkable as well. So has, by the way, hardware architecture led to a lot of improvement. So there has been advances in all these areas. Those aren't the only places. And one of the great things about this class is that you can use whatever you want. Algorithms, well, hardware is going to be a little bit harder to do except to exploit it. But, compiler technology, anything you want to try to make the code run faster. But indeed, algorithms, and we will give a reading which will talk about the impact in time, that'll be a suggested reading on the Canvas website that'll probably be posted later today. Okay, so, but if you continue this plot, getting up closer, you see that in around 2004, 2005, clock speed stopped improving. It was the end of the Dennard era, or the Dennard era. I guess it's pronounced Dennard. The number of components kept on its pace of doubling every 2 years, so Moore's law continued, but they couldn't clock the chips any faster than 3 or 4 gigahertz, and that's where we're pretty much stuck today, unless you do exotic, cooling or something. And what happened was, in fact, things were getting hotter the faster they clocked it. This is a slide that I've reproduced that one of Intel's vice presidents produced at the time, showing the problem in graphical terms. The transistor junction temperature at that point was hotter than a hot plate. Hot plate is what you boil a pot of water on, so that's pretty hot. But in just a couple of years after 2004, Intel predicted that if you scaled clock speed as had been done in the past, temperatures would reach that of a nuclear reactor. And a few years after that, the temperature of a rocket nozzle, and then the surface of the sun. I'm told that's hot, but frankly, I have no direct experience of it. If they tried to clock chips much faster, they would simply burn up. And although you might be able to do things to put off this trend slightly, it was pretty clear they'd hit a wall. And so we no longer saw clock frequencies increasing. But it turns out that Moore's law was continuing. We were getting more components on a chip. So the vendors did something clever. They said, oh, well, we can't use miniaturization to clock chips faster. Dennard scaling is over. But we have all these transistors being produced in accordance with Moore's law. Let's put multiple processors on the same chip. And within just a few years, all microprocessor chips, more or less, were multi-core chips containing multiple processing cores. Okay, your computer laptop probably has a minimum of 4. Moore's law now potentially provides a doubling of the number of processing cores every 2 years. But this solution came with a problem. So here you see the number of processing cores went from just 1 before 2004 to over a dozen in just 10 years. And as I say, it created a problem. Before 2004, virtually all software was written for execution by a single processing core. After 2004, you potentially have more performance due to more processing cores, but you must rewrite your software to take advantage of them. And the architectures are vastly more complicated. There are way more performance features, many of them requiring you to rewrite your legacy code. Performance is no longer free. Here's an analysis that we did of the commit laws from major open source software projects. The data isn't completely clear for every project, okay, but most show an upward trend of attention to performance. Okay, so when you look at the word core, as in multi-core, you see it's increasing for Mozilla. sorry, I'm sorry. This is for the Mozilla Core, which is a collection of tools that Mozilla makes. Mozilla is the ones who make the Firefox browser. And you see that they mention performance going up. Same for MySQL. OpenSSL is a little dicier because they're really looking more at networking than they are at processor performance. And the Eclipse IDE, it's going up, maybe not quite as much. So the data isn't clear for everything, but most show an upward trend of attention to performance. I worked with the job search company Monster.com to analyze the interest in software developer job announcements over time. And here's what we ended up with. So in the upper left, we have jobs mentioning performance, upper right, optimization, then parallel, then concurrency. And as you can see, shortly after 2005, performance-related keywords became more prevalent in job advertisements. People were starting to get more and more interested in performance. We can take a short break here, see if there are any questions. You should feel free to ask questions as we go through, and then I can just deal with them at breaks. So maybe I'll go forward, and then, if there are, Jonathan, if you can interrupt me if something comes that wants me to go back. But
sure thing.
We want to make sure we keep on schedule here. Well, if that wasn't enough, now, in this day and age, Moore's Law is over. Okay, we've hit another roadblock. We cannot miniaturize much more. We are not doubling every 2 years the number of transistors on a chip. So here's where we are now. Intel achieved 14 nanometer process in 2014. So doubling every 2 years, according to Moore's Law, means that Intel should have achieved 10 nanometers in 2016, 7 nanometers in 2018, and 5 nanometers in 2020. The reason it doesn't go the doubling in 2 years is because this is a linear scale, so you have to square it in order to see what the what it means to have the to double the number of transistors. But Intel did not actually release 10 nanometers until 2019. It took 5 years for what historically has only taken 2 years. And the situation is bleak for semiconductor technology. It will no longer give applications free performance. And that's a bummer. The party is ending. But it's been so much fun. Why can't Moore's Law go on and on and on and on? Rats. Well, it's kind of because of physics. Wires can get only so thin. Now, the ancient Greeks thought that matter was infinitely divisible. You could keep cutting it in half. But we know today that's not true. And in particular, at subatomic scales, the material properties of matter break down. No one knows how to make a wire that's thinner than an atom. Okay, things just change. Now, the silicon lattice repeats about every 5 angstroms, which is half a nanometer. And technology roadmaps generally think that before we get to things of that scale, we're not going to be able to build transistors at around 5 nanometers. And we're currently at 10. So that would be 2 more doublings, 7 and then 5. Now, they may be able to shrink feature size below that, but the transistors themselves are unlikely to shrink, and it's going to get progressively harder So we will get a little bit squeezing out of the existing technology. But the printing press is grinding to a halt. Semiconductor technology is no longer going to provide free performance. So suddenly, performance engineering looks really interesting to people. And if you look at a modern multi-core desktop processor, or a server processor even, it's got parallel processing cores, vector units, caches, instruction prefetchers, a GPU, hyperthreading, dynamic frequency scaling, where they adjust the frequency depending upon the heat and so forth. And these features can be challenging to exploit by software. They were designed to give you performance, but it's just theoretical performance. In 6172, you will learn the principles and practice of writing fast code on these kinds of machines. So, do we have any questions? Because now I'm going to move on and tell you about the class. Even if we aren't receiving an improvement in transistors per area, will we continue to see a decrease in dollars per transistor, which could allow us to get more processors per dollar when space isn't an issue? Actually, the cost of transistors has actually flattened and even gone up for a few years now. We are not getting cheaper transistors. So maybe there's that possibility, and certainly there are things like scaling out, but that's parallelism as well. And there are a lot of solutions to getting performance besides just writing fast code. But it turns out that software is one of the most interesting places you can understand how to get fast code. Okay, good. So let's talk about how we're going to run this class. So that's pretty much a summary of what the setting is. And we're going to do a case study. Professor Reagan Kelly will do a case study in just after I go over the administration issues. This course information handout is on the course website. And if you don't have it, don't worry about it. And let's see, can I share that? There we go. Okay. So this is a handout that basically goes over, and the first thing I want you to do is to read the course information handout thoroughly and completely. And very important, sign up for class resources and recitation sections at this URL by midnight tonight so that we can get you the resources. If you don't sign up here, you won't be able to use the class resources. You won't be assigned a section. The registrar may have offered given you a section assignment, and ignore those. Those don't matter. The sign-up form asks you for your preferences. Homework 1, which is going to familiarize you with the tools, you should do by Tuesday. And if you're unfamiliar with the C language, we're offering an optional presentation, Introduction to the C Language, on Sunday at 2 p.m. to 4 p.m. Via Zoom, and the link is available through the Canvas website. This class is, the prerequisites are 6004, 006, and 031. Basically hardware, algorithms, and software. The course programming language is C with the OpenSilk task parallel extensions. If you do not know C, as I mentioned, we'll have a tutorial on that. If you know Java, you'll find C is similar. If you don't know either Java or C, you should definitely attend the tutorial. This term, of course, we're going to hold the class entirely virtually. And for students in distant time zones, we'll record the lectures and recitations, and we'll make whatever accommodations are necessary to help you do well in the class. And yes, the tutorial will be recorded as well. So if you can't make it at that time, we'll try to record everything we can to make it available. But it will be better to attend in person generally, because you'll be able to interact. We have a fairly good-sized staff. We have 2 lecturers. We have 2 part-time lecturers who will mostly be doing things behind the scenes. We have 6 teaching assistants, and we have some lab assistants, including, hopefully, we can get a couple more, but we're good with what we have, and Cree Bruins will be our administrative assistant. Most of the things you want you can access via Canvas, the course management system, and that includes Piazza, which is our forum, the Slack channel, which I hope a bunch of you are on already. We will be using the MIT GitHub code repository, and you'll be submitting assignments through Gradescope. Generally, let me just say that we'll generally use Piazza rather than email for communication. You want to make a private post on Piazza if you want to talk to the staff. If you try to send us email, I tell you, my email box gets so full, and it's likely to be lost if you send it directly to me. So make it a private post, ideally to the whole staff, and then somebody can get back in touch with you as quickly as possible.
And same thing for Slack. I think our intention is that the Slack is for real-time communication like we're doing during the lecture right now, and for like group collaboration and stuff like that. But we're not going to commit to handling Q&A on Slack. It's a lot easier to track on Piazza.
Yeah. And by the way, I encourage you to chat with each other during lecture. You know, one of the real problems with Zoom learning is the degree to which it cuts off peers. You know, I've never minded when students, you know, quietly, as long as they're not disturbing their neighbors, chat with each other in lecture. Hey, what did he say? What does he mean by that? That kind of thing is really helpful when you're learning. And we don't have a really good peer communication system, but I encourage you to use Slack or your cell phones or whatever during lecture to talk with each other. Let's see, the lectures, generally people do better if they attend lectures regularly rather than trying to catch up on all of them at the end of the term. Everything we talk about in lectures is fair game for homework, projects, and quizzes. We will have regularly scheduled recitations on Fridays. There's 6 sections at these 3 times, so we'll have multiple sections at each time. These will be taught by a TA, and they are mandatory. Although, if you can get everything checked off during the recitation, you're free to leave early as soon as you've got your things checked off. Generally, they're going to go over the homeworks, and so you'll find it's kind of like having part of recitation will be some presentation, and part will be you trying to go through the homeworks and getting help if you need it. Our goal is to help people do well. We'll have office hours Sunday through Wednesday, 5:30 to 8:30 p.m. All these times are Eastern time. If you are not in the Eastern time zone and that time is not convenient, let us know and we will make some accommodations. We'll set up a queuing system to match you up with online staff help. And we'll also show you on the course calendar when things don't work. The grading is, we have 9 weekly homeworks, 2 quizzes, 4 projects, including a capstone project, Project 4, and class participation, which I'll mention as we go through the things that contribute to class participation. In particular, posting on the forum is good for class participation. So is sharing your code with the class. All the projects, all the homeworks are required. If you don't turn them in, you will have to talk to us to avoid failing the class. And we will help you perform well, and we have a very, I think, flexible late policy. So generally, we recognize that things may come up, and you're going to have a budget of 3 total late days to use as needed on homework assignments, and you can allocate those as you want. There's some things that can't be extended, like the beta and final project submissions, because those we need to turn around and get performance data back to the class immediately. But other things generally can be submitted up to 2 days late. So if you need to do that, just let us know and how many late days you intend to use, and that applies to your whole team. If you go over your budget, you're going to have to talk to S-Cubed about late work. And in addition, if you consult the EECS CommLab, we give automatic 2 days extension that doesn't count as part of your budget on your write-ups. If it turns out that something comes up, please let us know. If you communicate with us, we can accommodate, okay? We especially if you do it early enough, okay? If you know early enough that there's going to be a situation, let us know. We will try to work things out for you. Don't just miss assignments. But you do have to do all the work in the class. The CommLab can improve the quality of your project write-ups, and people can help you write things better and more clearly, and that generally will help you get a better grade. And so if you want to use that, you have to sign up a week in advance. I think maybe it's 5 days before the write-up deadline, and then you get an extra couple days for the write-up deadline. These are the tentative deadlines, and everything will be in the course calendar. But these, I believe these are accurate, but you know, this is COVID time. We don't know what things we're going to end up facing. So we may extend them or whatever. There are 9 homework assignments. They're intended to give you hands-on experience with tools and other practical topics. And they will help you complete, they help you evaluate your understanding of the project. There are 2 quizzes. The quizzes will be held during regular lecture time. Please mark the dates, and if you have a conflict, let us know. It's not an acceptable conflict to say I've got another class at the same time as this class. But if you have an issue, please let us know. And in particular, job interviews don't constitute a reasonable excuse to miss class. The quizzes will be open book with no outside collaboration, and we're currently working out how we do that, since we've never done online quizzes. And there's no final exam. The bulk of your out-of-class time will be, in fact, actually it's the bulk of your time probably, will be spent on the 4 projects, and they get more and more interesting as we go along. The idea for every project is the same. You're given a correct but inefficient program, and you've got to make it run as fast as possible. Each project has a beta submission and a final submission, plus there's a design submission for project 4, and there's also a design code review. You'll work in pairs to complete projects 1 through 3, and you'll be assigned a different random classmate as your partner for each project. So it's important that you sign up. For project 4, you'll be able to form a team of 4 with partners of your own choice. Now, this policy is a little bit different from what we did last year, and there was some discussion on it in Piazza, which I encourage you to read. But this is the way we're going to go forward. We've tried to weigh all the alternatives, and I think this is the fairest. There is not a de facto IDE, but I believe we will try to set up VS Code as a standard thing that people can use. And the 4 projects build on each other in sophistication, but not in, you don't need the code of one to apply to the code of the next. And there are 4 people in the final groups. Yeah, if you realize you have a conflict, submit the recitation form again. And but it'd be a good idea to alert us. There's a thing on there that says, do you have anything more? Alert us that this is a resubmission, since I don't think we have anything automatic to handle that. Those are all questions off the Slack. This is an overview of the 4 projects. I'm just going to talk about the 4th one, which is you write an AI bot that plays a 2-player board game. It's a lot of fun. It's a lot of fun. And you're going to need everything to do it. It's a lot of fun. As with all of the projects, you're not competing with each other. I don't grade on a curve. But we're going to have an exhibition tournament for fun after it over to see how you compare against each other. Okay, but you will not be competing with each other. I don't believe one student should get a worse grade because another student got a better grade. That's just not how and that's MIT policy as well. Now, a really valuable part of this course is the MIT Posse. We recruit senior software engineers from industry to help review your code, help you write better code. Okay, and we call these the Masters in the Practice of Software Systems Engineering, or MIT Posse, best acronym I ever came up with. And they will review your code and comment on its design, structure, and style, because simpler, well-designed code is easier to performance engineer. The MIT Posses, the deputies that we call them, don't participate in the grading process. But we will evaluate your participation in the design and code reviews to determine the MIT portion of your project grade on each project. We want you to perform well in the class, and they can help you write better code. They each are volunteering, okay? All have, they're from all the top companies, okay? All the places you might want to get a job. And all have extensive experience with on-the-job design reviews. So please accord them your greatest respect. They're volunteering their time. You can learn a lot for them. Okay, be professional, punctual, prepared, gracious. Thank them. Okay, they are not allowed to recruit during the class, but when the class is over, you're welcome to talk to them about jobs at their companies. The project structure, as I mentioned, has a beta submission, a code review with a deputy, and a final submission, except for Project 4, which also has a design plan. And you also have to submit a write-up, which is due typically the day after the project is due. Each project is a good. Will tell you all the details you need to know. So you're not competing with each other. Now, the first thing you do once you get a team project is you need to get a team contract, and we'll be more explicit about this, but it should answer questions like, how are you going to communicate? If one person decides to drop, what obligations they have to their teammate or mates? How will you divide the work? How will you review each other? How will you manage your code branches? What expectations regarding team grade do you have? Because you're going to be graded as a team. And if there are differences, is it acceptable for some team members to do more or less work than the others? If your team has problems working together, and that indeed may happen with random matchings, and you don't have anything in your team contract, it'll be more difficult for the course staff to help you. And your TA will review your team contracts and let you know of any concerns that you see. Okay? So you need to set expectations with, who's it going on. We can see who you're matched with. And if somebody is, we will evaluate and see who got matched in the first 3 projects with weaker partners. And those people we will compensate for. We can tell that based on the overall performance of people in the class. And that will be taken into consideration, okay, for your grade. For the beta, you basically just focus on creating a correct implementation and developing a good set of tests. And you try to make it go as fast as possible, but we're generally going to give more weight to the performance of your final submission. And then after the beta stuff has been released, we're going to anonymize it and post it online. So don't put in personal details. And you'll be able to see how everybody else in the class did. Okay, you're not competing with each other, but it's a great opportunity to look at other people's submissions and learn from them. And you can borrow ideas for your final submission, but you may not steal code outright. Okay, a good rule of thumb is to avoid copying is to leave a significant interval of time between when you look at somebody else's code and when you write your own version. After that, you're going to have the deputy comment on your code. Then there's a final submission. We will give a benchmark for what you need to meet in order to do well on the final submission. It'll generally be an aggressive one. And then you have the write-ups. And so for team dynamics, and this I can't emphasize enough, you have to make sure that everybody contributes. I do not want to see commits that are only from one person's Kerberos. Okay, we want commits to be balanced among the team, even if your team programming and team coding, pair programming, which we will encourage you to do. We'll talk about that and we'll encourage you to do that. And if you do feel that your partner is not pulling your weight, please let us know as soon as possible via private post. Okay, and we will compensate. In addition, every week during the term, on Thursday, you must submit a short, 1 paragraph is sufficient, personal status report. And it's basically your personal summary of what happened in the course since your last status report. Okay, and here's some of the things you can talk about. Your impressions of the past week's lectures and recitations. I hated that. I hate the random matching. I love the random matching. I met somebody I never saw before, whatever. And talk about your project partner or study group. Okay. What interactions you've had with your MIT Posse deputy or course staff, and identify them so that we can know what you're talking about and how you feel you're working, and things that might happen outside that had an impact on your work. Okay, I had a huge test this week, and that really compromised what I thought I could do in the class. We want to know that. It helps us to give you a better shake and a better grasp. Now, honesty is extraordinarily important, and we take it very seriously. We write the rule is you can't cheat. So I want you to read this carefully. If we do, we have a very strong motive to go straight to the Committee on Discipline, and then you face the possibility of expulsion from MIT and other punitive actions. The reason that we have such a strong statement here about what we will do is because I believe it is my duty to protect all the overwhelming majority of people in the class who do not cheat. And I do not want to be in a position to where they are unprotected from cheaters who look at doing well. Now, you're not competing in this class, but you may be competing for jobs down the way. And I do not want somebody who gets a false A in my class to compete with somebody who gets an A. Okay? I want people to accept the grade that they get. Frankly, if you get, any passing grade in this class, employers want you. Okay? So please read this. If you're unsure about anything, let us know. Generally, you can use general conceptual material cited if you can. You can collaborate, but you've got to write things up on your own. And make sure you're turning in your own work. If you can't explain what you're doing for the work that you have in, we consider that to be a violation. You have to be able to explain what you write down so that we know that it's your own work. Okay, if you need help, we are here to try to help you. So try to make a reasonable attempt on your own, but do not get stuck. Come to us. Come to office hours. Okay? And let me just remind you, you'd need to get started early on things. Programming assignments often take longer than you expect, even after taking into account that programming assignments often take longer than you expect. Okay, that's a play on Hofstadter's law, which Doug Hofstadter got from other people as well. So if you need things, we're here to try to help. We have a lot of staff designed to help you do well in the class. I want people to learn this stuff. I'm not interested in policing people. I'm not interested in grades particularly. Okay, but I do know my responsibility as a faculty member, and that means I need to protect the evaluation part of the class for the other people who are in the class. This class is fun. People tell you they put a lot of work, but it is fun. Okay, this is one of the most fun classes you're going to have at MIT, coronavirus notwithstanding. So at this point, I'd like to turn things over to Professor Reagan Kelly, who's going to take us back into the material of the class and show you a case study of performance engineering. Jonathan, take it away.
Okay, great. So we're running pretty far behind schedule at this point, so it's pretty likely that we're going to spill over into the next lecture, but I'm going to do my best. Okay, so like Charles said, we're going to start the remainder of lecture and start diving into the technical material class by looking at a performance engineering case study. And I'm going to go through this pretty fast, even faster than I was intending, like I said. So I don't really expect you to understand everything today, but a lot of what we see and do today, and maybe at the beginning of next lecture, is exactly the kind of thing that we're going to do in the rest of this class. So right now it might be a bit of a blur, but by the end of the semester, you'll be able to go back through this lecture and really understand pretty much everything I'm about to say. And the problem that we're going to look at is at its core something really simple. We're going to look at just multiplying a couple of matrices. So mathematically, matrix multiplication is just this simple summation formula, which you'd see in any linear algebra class. So each entry in the matrix C here is the dot product of a row of A with a column of B. So each entry of C is a sum of n terms, where n is the size, the width and height of our matrices. And each of those terms is the product of an entry in A with an entry in B. And this is really simple, but it's ubiquitous in numerical computing and machine learning and other things like that. So for example, if you've done any deep learning, this is the core of any convolutional or fully connected layer in a neural network. Yeah, so I'm not going to stop to ask if anyone's written code to do matrix multiplication, but I imagine a few of you probably have. For today, to keep it simple, we're going to be working just with square matrices. So each matrix here is n by n, and we're going to assume that that n is a power of 2 to keep our code a little extra simple. And then if we look at the algorithm, we think about this from like an asymptotic perspective. We think for a second, we can see that each entry in C takes order n time, since there's n of these multiplies and adds here. And then there are n squared entries in C, so the total amount of work we're going to do is n cubed. All right, so that's what we're going to try to optimize. Sorry. And we're going to look at implementing that on a machine roughly like the ones we'll be using in the class for our performance benchmarking. So this is an Amazon AWS C4 8X large instance. It has a clock speed of about 3 gigahertz. There are 2 processor chips. And on each of those chips, there are 9 cores. So we have 18 total processor cores. And this is that emergence of multi-core parallelism that Charles was talking about over the last decade. In addition, each of these cores is actually hyper-threaded, which means that they can execute instructions from 2 threads in parallel. So 36 total parallel threads. And to actually execute those instructions, each of these cores has a floating point unit that can do 8 double precision fused multiply add operations per cycle. So fused multiply add means a single operation that multiplies 2 numbers and adds them to a third, which if you think about it is exactly the thing we have to do inside our matrix multiplication. And we can do all that at a throughput of 8 of these operations per cycle. So 16 total operations if we count the multiply and the add separately. 16 total operations per core per cycle. Times 18 cores, times 2.9 billion cycles per second. If you multiply that out, it's a little over 800 gigaflops, 800 billion floating point operations per second. So that's pretty impressive, a lot faster than computers we had a couple decades ago. And this machine also has a deep memory hierarchy with 3 levels of cache. So caches are memories that are smaller and closer to the core than the big main memory, so they're faster to access than our big main DRAM. And we'll talk more about caches and how they're organized later, but the key idea here is that if you can read and write most of your data in these small cache memories, it's going to be a lot faster than if you have to touch main memory. All right, so that's the algorithm and the machine that we're going to be looking at. So let's sit down and try to write some code for this. Let's start simple. So we can start just with some Python. So this is a nice simple language that you've all used in the undergrad curriculum by now, I believe. And this is the complete code to implement the whole thing, including setup. So we first initialize the 3 matrices. We're putting some random values in A and B and some zeros in C. Then we start a timer. And then the part that we actually want to benchmark is just this triply nested loop where we actually do the computation. So for each I, J, and K from 0 to N, we multiply A, I, K by B, K, J and store the result into C at I, J. And we're accumulating the result into C at I, J. So when we're done with those 3 loops, we measure the time and then we print it out, see how long it took. That's it. So now I want to ask you to think for a second about how long you think this takes to run. Let's think about that for a second. So how many operations are there in a 4K by 4K matrix multiplication? How many times do we go through this loop nest down here? So you can see there's 3 levels of the loop, each over n. N is 4,000. So we get 4,000 cubed. 1,000 cubed is a billion. So that's 4 cubed is 64. So that's 64 billion multiply adds. So that's a lot of operations. But remember that our processor runs at about 3 billion cycles per second. And each core can do 8 multiply adds per cycle. And we have about 18 of them. So if you think for a second about roughly how long this should take, I want you to go ahead. We're going to post a poll on Slack asking what you think. Do you think it'll take 6 microseconds, 6 milliseconds, 6 seconds, 6 hours, or 6 days? Because we get a lot of votes for 6 seconds. It seems to be dominating everything. A few people think 6 hours, and a few people think 6 days. All right, so I think you guys are, and 1 or 2 people think it's going to be in the milliseconds range. So I think most of you are doing good back of the envelope math here. But it turns out that the running time of this code is actually 21,000 seconds, or about 6 hours. So what do we make of that? Is this fast, or should we expect more from our machine? So to understand that, I think the first thing we want to do is go do a little back of the envelope calculation. This is basically what I was hinting at, thinking about how big our machine is and how fast it ought to be able to run before we started the poll. So we get out our envelope. We've got those 2n cubed operations. It's about 2 to the 37 total floating point operations. The running time that we saw is about 21,000 seconds. And so if you divide that out, you see that with this Python code, we're getting about 6 million floating point operations per second, or 6 megaflops. But if you remember, the peak performance of this machine is 836 gigaflops. So that's 100,000 times more. So we're pretty far from using our machine to its full potential. And really precisely, if we divide it out, Python's getting 0.00075% of peak performance. So I think we can do a little better. So this is where we get to do some performance engineering. But where do we want to start? Well, the first thing you might think is, if Python's really slow, you might have heard that Python's slow. Maybe we should try another language. Maybe there's other faster languages. So let's try Java. So this is the same thing in Java. Again, the top is all just initialization and timers. And we're really only interested in this part of the code that does the actual work. It's essentially the same, just Java syntax for those loops. Now, how fast does that run? Turns out just switching to Java gets us down to about 2,700 seconds. So that's about 8.8 times faster than Python. So that's a pretty good start. But remember that we were 100,000 times off peak. So we've closed most of one order of magnitude, but there's about 4 more to go. So what might we do now? So changing languages helped. Maybe there's an even faster language we could try. So, I've heard, and you might have heard too, that C is pretty fast. That's the language we'll be using for most of this class. And it's also what, most things like operating systems and video game engines and stuff use. So maybe that's a promising place to go. Now, once more, the code is a little different on the surface, but the core loops look pretty much the same. And then if we run that, how fast is it? Using the client compiler from LLVM5, which is a slightly older version, because we ran this experiment a couple years ago, but is a slightly older version of exactly what we're going to be using in this class. It takes about 1,150 seconds. So that's about 2 times faster than Java and 18 times faster than Python. All right. So we're starting to see a lot of different numbers. I've thrown a ton of different numbers at you already with just these 3 variants. So to keep track of all this data, let's organize it a little bit better. Let's make a table. So here's where we are so far. We have version 1 in Python, then we have Java, and then C. And in addition to the raw running time, we have the relative speed up of each version over the one before. And the absolute speed up relative to the Python baseline. And then we also have the gigaflops and the percentage of theoretical peak performance in our machine. So we're still really far from peak, but we've already gone from 0.007 gigaflops with Python to 0.119 with C, almost 20 times faster. So the first question this raises is, why is C so much faster than Python with code that looks almost the same, at least in those core loops where we're spending all of our time? And one part of the answer here is how these languages are actually implemented. So you might know that Python's interpreted at runtime, while C is compiled directly to machine code before we ever run it. And then Java turns out is somewhere in between. So it's compiled ahead of time to a virtual machine bytecode, and then that bytecode is just in time compiled to machine code while it runs. Now, you've probably heard a little bit about all these terms before, but what does that really mean? So first, what's an interpreter? So an interpreter is a program that runs another program by reading each statement of the program it's running, interpreting what it means, like deciding what the next statement needs to do, executing logic to perform that statement, updating some program state, and then going on to the next statement and doing it all over again. So instead of just executing the logic of our program directly, all the multiplies and adds, an interpreter has to spend lots of time at runtime dynamically reading the program and deciding what to do. So it's sort of like a Turing machine that's reading our program off a tape and deciding what to do each cycle. So it has to spend most of its time at that meta level reading and interpreting the tape rather than doing actual useful work. Now, this kind of language implementation is nice in some ways because you don't have to compile at all. So it's both a lot simpler to implement. And as a user, you can just run your program immediately without having to wait to compile anything. And it's also easy to support things like dynamically generating and changing your code at runtime. We've seen that it's slow because of all that interpreter overhead. If you're willing to invest a lot more engineering effort in building your language, you can also make this go faster by using a JIT, or just-in-time compiler. So with a JIT like Java, usually you interpret the code the first time you see it, but any code that you run over and over again, like the loops inside our matrix multiply, get dynamically compiled and optimized into fast machine code that we can run without any of the interpreter overhead. Okay, so those are some of the basic differences between Python, which is interpreted, Java, which is JIT compiled, and C, which is fully compiled ahead of time. And there are also big differences in how these languages represent objects and arrays in memory, and all kinds of other things in their implementation that heavily impact performance. But they pretty much all align with this axis where Python has the highest overhead, Java is in the middle somewhere, and C is the lowest. All right, so any questions so far? I'll pause for a second, see if anybody raises anything on Slack. All right, seems like one or two people coming in. So Gannon asks why these languages chose these methods. So I alluded to some of the reasons. So like I said, an interpreter is often a much simpler way to build a language implementation than a compiler. In old 6001 curriculum, the first semester class at MIT had you implementing an interpreter for Scheme and Scheme as a single project. Implementing a JIT compiler or optimizing offline compiler is a much bigger endeavor. But it's also possible if you're dynamically generating and changing code at runtime, which is actually common in things like JavaScript and Python, it's how they get a lot of their rich features that let you build really powerful and productive libraries. It's much easier and faster to add new code or change code in an interpreter than in a compiler that has to invest a lot of effort optimizing and generating machine code for that code. So those are a few of the reasons. Somebody else asks, couldn't you just build a compiler for Python? And the answer is, it turns out to be really complicated because of the design and fundamental dynamism of the language. A bunch of people have tried and not gotten very big wins. So the design of the language and the runtime model turns out to play a really big role too. Okay.
Yeah, Python decides it's going to spend part of its performance budget on making it very interactive and flexible and simple and dynamic. And if that's not what you want the program to do, then they've misapplied the dollars that could otherwise go to your performance purposes.
Yeah, absolutely. And there's a lot of contexts where that dynamism is really useful. And if you're writing code like in a web server that's bottlenecked on I/O rather than compute, often this interpreter overhead actually doesn't really matter because you're spending most of your time just trying to make a few simple decisions to keep how you're going to fetch data off disk and feed it to a bunch of web server clients or something. The overhead on doing actual compute isn't really your bottleneck. So there's contexts where it can make a lot of sense to get that more dynamic flexibility, gives you a more powerful and productive language. And maybe the performance overhead doesn't matter as much, but it depends on the application. And matrix multiply is not a case where that makes sense. Okay. So our C is faster than Python, but even with C, we're really far from peak performance still. So clearly performance engineering doesn't just mean write your code in C instead of Python. So now what else can we do? Let's go back for a little bit to the core loop code. So now if we look at this, this inner code that is the main bottleneck that we're trying to benchmark, if you look at these loops, one thing you might notice is that it actually doesn't matter in what order the loops are executed. So this is going to compute the same thing, whether we go through I, then J, then K, or I, then K, then J. or k then j then I, or even if we go backwards or in random order across all these loops. So one question we can ask is, would this code go any faster if we just iterated in a different order? And just thinking about the ways that we can reorder these 3 loops, there's 3 factorial or 6 total permutations. So we might want to ask, are some of these fast and some slow? Still doing the exact same total amount of work, all the same operations, just in a different order. So could changing the loop order like this possibly make a difference? So once again, let's test stuff, make a table, and see if we can tell if there are any patterns. All right, so if we do that, we try all 6 different variations and benchmark them, we can see that the IJK order that we started with runs just over 1100 seconds like we saw. But if we just switch K and J, it runs in only 177 seconds. And further down the table, you can see that there's even worse orders that take as much as about 3,000 seconds. So just changing the loop order here makes it 3 times slower or 6 times faster than before, or about an 18x difference between the worst and the best. And what does 18x mean? So if you just think, if we're at Google running a machine learning model on a whole data center to serve, the web requests and ads to the entire world, machine learning these days, again, is basically all about matrix multiplication. We potentially need 18 times fewer machines in our data center to serve the same number of users, just by changing the order of these loops. All right, so what's really going on here? Like I said, we're doing the exact same set of operations, just in a different order. But how could this matter so much? I'm wondering what people think. Maybe post some ideas in Slack if you have any thoughts about what might be causing this difference. Yeah, so great answers. People are saying caching, data locality, et cetera. And that's exactly right. So if you remember from computer architecture like 6004, our processors have caches. So all reads and writes to memory go through these caches. And the caches don't deal with individual bytes at a time. Instead, to get higher bandwidth, they move data around in bigger blocks called cache lines. So on our machine, the cache lines are 64 bytes. So anytime we want to move a piece of data between memory and the cache, it has to move a whole 64-byte chunk. And our caches store the most recently accessed of these chunks. So the idea then is, if we access the cache line recently, that's the best indication that we have. We don't have a perfect oracle, but that's a good guess that we might read or write that same chunk of data again soon. And reading or writing addresses that aren't in the cache, what we call a cache miss, is much slower since we have to read it from off-chip main memory. And it can literally take more than 100 times longer to access data from main memory than from like the L1 cache. All right, so what does all this mean for our matrix multiply code? Well, to think about it, first we need to think about how our matrix is laid out in memory. Because that's going to determine, given the iteration order through the different matrices, that's going to determine how we're walking around over addresses in memory and what data is going to be pulled into the cache in what order. And it turns out that C lays out arrays in what's called row major order. And what that means is that when you look at the memory for the matrix, walking up the memory addresses in increasing order is what we see on the bottom of the slide here. You first see all of row 1, then right after that you see all of row 2, then all of row 3, and so on. Now, how's this going to interact with our memory system? So when we access the first element of row 1, we're actually, remember, going to be loading a whole block, a whole cache line of the next 64 bytes of row 1 into the cache. So if we next access the second element of row 1, it's already going to be sitting there in that cache line that we just fetched. But if instead we access the first element of row 2, if we walk down the columns, that's really far away in memory. We're going to get another cache miss immediately. And if we scan down the columns in this order, we'll get a cache miss on every single one. So let's take a look at what happens in this access pattern. So here's our original code, and here's the layout in memory of the 3 matrices. So now let's think about what happens when we just go through this innermost loop over K. So we're going to run our multiply add at 4,000 different indices of K, but I and J are going to stay fixed because we're only considering one iteration of I and J. So we look at where that's going to touch in C. C is only indexed by I and j. So for every iteration of k here, we'll be updating the same single entry. So that has great spatial locality. So we're going to hit in the cache for every single iteration of k. We're only accessing one value over and over again. But if we look at A and B, we see different access patterns. So in A, we're walking across the row. So that's still okay. It's not as good as we're using the same value, but remember our cache fetches a whole cache line of 64 contiguous bytes every time there's a miss. So in this case, after the first entry in a cache line, we're immediately just going to go on and use all the rest of it for the immediately following 7 iterations. So we're only going to do 1/8 of our iterations having a cache miss, because there's 8 double precision floating point numbers that fit in the 64-bit cache line. All right, that's not so bad. But what's going on with B? So in this case, it turns out that we're going down the column of B, like I was alluding to. So we're bouncing from the first row to the second row to the third. And each of those single elements that we're reading is 4,096 elements apart in memory. So we get basically no cache locality. It has really, really poor spatial locality. And what do you think this does to our performance? Maybe it's not so bad. Maybe we get some kind of average of excellent, good, and poor, and maybe it's kind of good. But like often happens in performance engineering, you don't get the average. Instead, you get bottlenecked by whatever is kind of the critical path, whatever's worst, and that winds up completely dominating your performance. And indeed, that's what we see here. So I think, like I said, unfortunately, we ran a bit behind today. So I don't want to run too far over. We'll probably pick up with the rest of this investigation on Thursday. But I want to reemphasize that it's really important that you sign up for, fill out the class section information sign up so that we can figure out section assignments, project groups, and all that kind of stuff, and get the assignments rolling. So please do that today as soon as you can. All right, thanks.